So in this lecture, we're going to discuss how to prove that one set is a subset of another one. And we'll also discuss how to prove two sets are equal, which is actually quite a bit trickier than it sounds. So before we do that, let's start with sort of a warm-up. Yeah, we'll call this number one. So this is proving that something is an element of a set. So remember, this is our symbol for is an element of. Okay. So how would you prove that something is an element of a set? Well, the idea is fairly simple. So to show X is in S, some set S, we need to, well, how should I say this? So we need to show that it satisfies the condition, whatever the condition is, for belonging to S, belonging to the set S. And you might recall we had what was called the set builder notation. So a lot of sets are defined in terms of the set builder notation. So an example of that would be, let's let S be the set X in Z, so all the X in the integers, all integers, such that X is of the form 2k plus 1 for some k and for some integer k. Okay. What this is right here, this is the condition for belonging to S. So that's the condition for belonging to S. So for example, if I wanted to show, let's see the number, what is a set, by the way? This is the set of all odd numbers, right? Odd integers. So let's say we want to show that specifically the number 17 belongs to S, and it does, but that's because it satisfies the condition for belonging to S. In particular, it is of the form 2k plus 1. Let's actually show that. It's 2 times 8 plus 1, and 8 is an integer. So there we go. So that's a bit straightforward, but it can be maybe a little bit harder. Let me try to think of a harder example. So how about this? So is 0.44444, etc., repeating in the rational numbers? Okay. And let's recall our definition of the rational numbers. The rational numbers are defined to be quotients of integers, so a over b, where a and b are integers. I suppose we also want, and we don't have a denominator of 0, so b is not 0. Okay. And you might have heard the fact that repeating decimals, these are all rational numbers. The irrational numbers are decimals that don't repeat. But how do we show that this actually is of this form, right? This is the condition we need to show. It's actually some integer over some integer. Well, we can try to write this as an integer over an integer. You might already know what that is, but here's how you might do that. So this is, we can write it as an infinite series of fractions. So it's 4/10 plus 4/100ths, right? Hundredths place, plus 4/1000ths, etc. And that's, well, what is that? It's 4/10 times, factor out the 4/10. So I get 1 plus 1/10 plus 1/100th. I have a geometric series here. So that's a geometric series. geometric series. And what's the sum of a geometric series? There's a formula for that. So 1 plus a squared plus a cubed. As long as this converges, this is equal to 1 over 1 minus a. That's the formula for the sum of an infinite series of this type. And we're assuming a is smaller than 1 absolute value. But it is here, it's 1/10. So we can use that formula. It's 1 over 1 minus 1/10, which is 1 over 9/10, so that's 10/9. And we have our fraction. Our fraction is 4/9, so that's the decimal 4/9. And this, now at this moment, it is clear that this is an element of the set Q. So that's a trickier example, but just to show the idea, right? So to really show this is a rational number, we need to show it satisfies the defining condition. Okay, so that was just a warm up for what's next. We're gonna now show how to prove a containment of two sets. So how to prove that one set is a subset of another set. Remember, this means is a subset of. Is a subset of. And here's going to be our strategy. There's a standard strategy. The standard strategy is you consider an arbitrary element of the smaller set. The one you're trying to prove is in the bigger set. So arbitrary element of, or here, let me give it a name. So an arbitrary element x in A. And what do I do with that arbitrary element? Then I show that actually x is also an element of B. As an element of B. And funny enough, I'm done if I do that. So wait, I just showed it for x. Like, how do I show the whole set of A is contained in there? Well, I'm doing it for an arbitrary element, any old element of A. So I'm not. X could just as well be any element in A. And when you think about it, this makes a lot of sense, because what does this containment really mean? Like this means it sort of means for every x in A, x is in B. That's really what that means. This is a collection of a set of elements in B, this A here. And so for A to be contained in B, that's what it means. And so this does it. So we show for every element in A. That's why we're picking an arbitrary element, because it's a for all. And we need to show that's in B, and then we're done. So for example, let's show that Z, the integers, is a subset of Q. Well, here's how you do it. You start with an element in Z. So let's let x be an integer. And then we need to write it in this form. That's easy enough. Since x is x over 1, right? That's it. X is in Q. Okay, and because x is arbitrary, we've showed that this entire set Z is contained in Q. Let's do another example. This takes a bit of time to get used to. So, in fact, I'm going to give you two sets. So my first set is going to be the multiples of 2. Let's call this one A. And then my second set is going to be the multiples of 4. And I'm claiming that one of these sets is actually contained in the other one. Can you see which one is contained? By the way, definitely talking about Z here. Our universe is the integers. So integers are multiples of 2, multiples of 4. just think about it this way. So any multiple of 2, is that a multiple of 4? Well, no. 6 is not a multiple of 4. Right? 2 is not a multiple of 4. 4 is. But any multiple of 4 is also a multiple of 2. So the containment is actually going to go this way. Okay? So that's, let's see, containment. B is actually contained in A. So let's show that. Let's prove that the set B is contained in A. Okay. Okay, and just to remind you, so what are multiples of 2? In other words, even numbers. They're x and z, such that this is good practice. Try to write this out on your own too. But, so for k and z, and this one is the same as these are the integers, such that they're the form 4 times k for some integer for some k integer k. Great. By the way, this is not necessarily the same k as that. Okay, this k is restricted to this definition here. Okay, so outside of this this definition, the k is not locked to the value that it took on here. Okay, so prove B is contained in A. First of all, here's a wrong proof, just to give you an idea. So wrong proof would be, we'll take an element of B. Let's take, for example, the number 8. That's a multiple of 4. And then I'll say, since 8 is 2 times an integer, what do we conclude? Well, we can indeed conclude 8 is an element of A. It looks like we did it. This doesn't work, though. That's because we only proved it for one element. We need to prove it for any element, every element. And so that's why we need to take a completely arbitrary element. So we should take an element just of this arbitrary form. So we're going to let x be an arbitrary element of B. Let x be, let me just emphasize that. So be an arbitrary element of B. Okay? And what does that mean? So x is 4 times an integer. X is 4k for some k in the integers. Okay? Then we need to show that this belongs to A. How do we show that it belongs to A? We show that it satisfies the defining condition for A. So we need to show it's 2 times an integer. We can split that 4 up into, so x equals 4k, which is 2 times an integer. 2k is an integer because k is an integer. So indeed, x is an A. And this really does prove it, because x was an arbitrary element of B. It's not just the number 8, for example. Like this x could be anything. Okay. Yeah, and just to emphasize the logic once more. So since x was arbitrary, we can conclude B is a subset of A. Let's put our QED symbol, because that feels like a complete proof there. Excellent. Okay. So let's do the next our next task, and this is the most complicated of them all. It doesn't seem like it should be, but we're going to talk about actually proving set equality. So proving 2 sets are equal. And so what does set equality mean? It just means the sets contain exactly the same elements. You can say, well, that's simple. You just look at the sets, see if they contain the same elements or not. This isn't so simple with infinite sets, though. So you can't really, this becomes hard to think about. Like, how do you actually prove two infinite sets are equal? Yeah, so this can be quite tricky, but there is a method that makes it much easier to think about, and that method is, so rather than, so this is the, rather than trying to prove A and B have all the same elements, just directly, we can use the following strategy, and this is a rather surprising idea, but it is a standard idea. So the first step is you prove that A is contained in B. You prove that A is a subset of B. And subset doesn't necessarily mean proper subset. It doesn't necessarily mean it's smaller than B. It could be exactly the same, right? That's why you often put this line here just to emphasize it could be equal. By the way, if you really want to emphasize it's a proper subset, like they definitely cannot be equal, you often use this symbol. You put a little cross through that line. If you really want to emphasize, so for example, Z is a proper subset of Q. Q has more things than Z. They're definitely not the same. But yeah, so first we're going to prove that this side is a subset of that side. Okay. The second step is you prove the exact opposite. Well, not really the opposite, but you prove that B is a subset of A. You swap these. Okay, you prove this side is contained in that side. And when you think about it, so together, this proves they're equal. Because if they weren't equal, then one of them wouldn't contain the other. So it's kind of a roundabout way of proving two sets are equal. And again, this, like, when I first saw this, I thought this was a rather shocking idea, and I didn't like it for quite some time. But now I've sort of gotten used to it, and this is an absolutely standard method. The nice thing about it is it breaks it down into two smaller problems where it's really clear what we should do. Okay, we have a strategy that we're always going to follow, and so. And that prevents you from thinking really hard about why exactly these sets are equal. You can save your brain power for more interesting parts of the argument, maybe. So let's do an example of this. Our example will be, we'll start with something rather easy to think about, or simpler to think about. So let's prove the sets. Let's do the same as before. So we'll prove the sets 2k plus 1 these are the odd numbers. You might have wondered why can't you represent an odd number like this instead? Like, why don't we do 2k minus 1? Well, turns out you can. These sets are exactly the same. So let's prove that these two sets are equal. They're the same set. They have the same elements. They're both infinite sets, but yeah, they have all the same elements. And let's call this one A and this one B. Okay. Okay, so step one first, we'll prove. Again, this is going to make it way easier to think through the argument. So we're gonna prove that A is a subset of B. Might be equal, but we're definitely going to prove that everything in A is an element of B. Okay, so here's how I start. I say let X be an A, be an arbitrary element. So let X in A be arbitrary. Okay. What does that mean? It means X is of the form 2k plus 1 for K and Z. For some integer K. Now I need to show it's of this form. Notice I wrote this a little differently than before. Just to kind of show the versatility of this set builder notation. So how did I write before? I was all the way up here. So this is the same set as this. I just wrote it a little bit differently. So this is a typical form of an element, and here's a condition. So it's 2k plus 1 where k is in z. It's a different way of writing it, but they're both equivalent. But yeah, let's actually show that this is of the form 2k minus 1. And you might be able to just think through this. I like to kind of work out an example on the side. It's not going to be part of my actual proof. But for example, 7 is 2 times 3 plus 1. What if we had to write it as 2 times something minus 1? I guess that'd be 2 times 4 plus 1. So 4, I need to go 1 bigger. So here's what I think I should do. I think I should say since x is, well, it's 2k plus 1, but I can also write it as 2 times k plus 1 minus 1, right? That's just the same thing. It's algebra. We conclude. What do we conclude? We conclude that x is an element of B. Great. And that proves that A is contained in B. Step 2. Next, we'll prove B is contained in A. Notice I'm kind of giving a guide to the reader. If someone's going to read this, just to show exactly what I'm doing. Otherwise, they might be confused by this. So I will let x be in B, which means x is of the form, now it's of the form 2k minus 1. I need to show it's of the form 2k plus 1. But yeah, we can probably just kind of duplicate the same argument. So x is 2k minus 1. Okay, how do we write that as, sorry, I shouldn't put that parentheses. How do we write that as 2 times an integer plus 1? Well, I think I should do this. So k minus 1 plus 1. I just rewrote that in a fancy way. Staring at this over here, right? So it's 4, it needs to be 3. So k minus 1, if you simplify that, you get that. So because it's of this form, of the form of something in A, see here's my new k, right? So it's 2 times something plus 1. These k's are not the same. Yeah, we conclude x is in A. Okay, let's add another sentence. So since, just to convince the reader, so since A is a subset of B and B is a subset of A, we conclude that A equals B. This is completely logically valid. Doesn't matter what the sets are. Yeah, you can show these two things, and that's always showing that the sets are equal. Because again, if they weren't equal, then one would have an element that's not in the other. So we're showing this. Okay. Great. Should we do one more example? Let's do a more abstract example. So I'm just gonna say A and B are sets. Not telling you anything about them. There's some sets. They could be anything. I want to prove the following identity. So prove that. And this will give us a chance to maybe review some of these set operations. I guess actually get some practice with them. So let's prove that A minus B is a set difference. Is the same as A intersect B is the intersection. So yeah, what are these things? A slash B, that's the set difference. The difference of A and B. So they're the elements of A that are not in B. So this means all the this is all the x in A such that x is not in B. Okay, so that's what that means. And what does this mean? This means all the elements in these are all the x such that x is in A and x is in B. It's the intersection. The other one was the union. This is where it's x in A or x in B. This is our intersection. And this is our set difference. Okay. Let's actually prove something about that. So this is sort of saying that how the difference and the intersection relate in this way. And this is really tough to wrap your head around if you just try to think about why they're equal. It becomes much more manageable if you break it down like this. So we have these two sides. So first, we'll prove we can choose either way. So we'll say, let's prove that the left side is contained in the right side. Then we'll do the opposite conclusion. Okay. Where do we start? We start by taking an arbitrary element of this. Okay. So we'll let x be an arbitrary element of this. So just let it be some element of this. Okay. What does that mean? Well, it means that x is in this thing, but not in that thing. So then, x is in A, right? We know x is in A for sure. And we know, and x is not in A minus B. Okay. Great. Okay, let's try to unravel this actually. So if x is not in A minus B, what does that mean? If x is not in A minus B, maybe I can go over to do some scratch work here. So if x is not in A minus B, just over to this side. Here's what it means for x to be in A minus B. It means x is in A, and x is, so x is like saying x is in A and x is not in B. If x is not in this set, then so this means well, it could mean x is not in A to begin with, and we don't even hit this, or this is not true, right? So either x is not in A or x is in B. Okay. So that's I'm essentially taking the negation of this. Okay. So that's the negation of this. Okay. Well, if I'm not in here, since let's just write that out. So since x is not in A minus B, we know that x is it's either not in A, or not either, sorry. It's not in A, or it is in B. But this is impossible, right? I would contradict that. So we know x is in A, right? Which means x must be in B, right? Because this is an OR, and we know this part of the OR is false. So for this to be true, we need x to be in B. So x needs to be in B. Okay. And we've kind of unraveled what this all means. The first time I did a problem like this, I remember it probably took me like a good half hour just trying to unravel all the definitions. Yeah, so where are we at so far? We know x is in A, so x has to be in B because of the OR here. But wait a second. If x is in A and x is in B, then X is in the intersection. So hence, X is in A and X is in B. So X is in A intersect B. So we've actually proved that this set is contained in that set. Okay. We're halfway done. So next, we'll prove the opposite containment. So we'll prove that A intersect B is contained in this one. It's contained in that one. Okay. And where do we start? We start by letting X be an element in this, an arbitrary element in the intersection. And I'm immediately going to write out what that means. So X is in, what does it mean to be in the intersection? It means X is in A and X is in B. Right, X in A and X is in B. Okay, let's think through this. We need to show it's in here. How are we going to do that? Again, these are the things that are in A but not in this. So we know X is in A. So to show, maybe I should just do this on the side, but I'm just kind of writing out my thought process. So to show X is in A minus B, it suffices to show X is not in A minus B, is not in this part. Because again, these are things that are in A and not in A minus B. And we know X is in A, so it suffices to show this. We don't have to show X is in A, we already showed that. Okay, so what does it mean for X not to be in there? Well, we already wrote that out, so i.e. X is not in A, or X is in B. Okay. Well, we're not going to have any hope of showing that, right? Because X is in A. We might be able to show this. In fact, we can immediately because X is in B. So since X is in B, we definitely know that X is not in A minus B. So these are things that are in A but not in B. Okay. But X is in A, right? So since X is in A, we showed X is not in this thing, but it is in that thing. So by definition, it has to be in A minus B. And that's it. That's complicated though. That's a bit complicated. We're done though. Like that is the end of the proof. Because we showed that set's contained in that set and that set's contained in that set. Okay. In this type of an argument, this takes some time to get used to, but just definitely wanted to show you one of these. It's called an element chase. You sort of fixate on this one element and chase it through, just unraveling the definitions. Try to show this on the other side, and then start here and then try to show this on that side. It's a bit of fun. It's pretty fun actually once you get the hang of it. Maybe I'll give you so I don't want this to be too long. I'll give you a practice problem you can try. That's maybe of a similar level as this one. So you can try this one. So prove that A minus B union C, again that means the things that are in B or C, is the same set as A minus B and intersect A minus C. So the things in this and that. Okay. So that's a good one for you to try. Maybe I'll just outline the argument. So first you need to show this inclusion, and that would start by suppose x is in this thing. That here I'll even write the next sentence. So then what does it mean? It means that x, for to be in this, it means that x is in A and x is not in B union C, etc. So you can try to fill in that. And then that'll be half of the proof. The other half, you'll show that starting with an arbitrary element here, you're contained in there. So that'd be a good one to try. All right, thanks for watching.